There's been a lot of permafrost questions, so I might actually, more than one person, I might talk about a little more than what's going to this talk, but so I'll talk about it. So my examples actually are mostly going to be ground permafrost examples for airborne electromagnetic data and geology applications. So, the project I'm going to talk mostly about and show data examples from is this Gulfstream Valley watershed project, and it's just outside of Fairbanks, kind of right in the backyard. So just a little context on how this project came about. This is a collaborative project with the University of Alaska Fairbanks. It's national science funded, and really the goal here is understanding and mapping permafrost distribution in the valley and why that's important in the project context and why is permafrost important. We'll go over a couple of those things. So the project's really interested in hydrology and changing hydrology as the permafrost melts or degrades. It opens up new hydrologic pathways. And of course, things that get funding these days are greenhouse gas emissions. So as you melt the permafrost, you create new wetlands, which can cause super emissions. And it's also known that underneath permafrost, there's nothing trapped. So, and they can document that by looking at the chemistry of the carbon ratios. And then permafrost, as we talk about it, it's essentially just frozen soils. Let's just step back one. So essentially, this part of Alaska doesn't have a lot. And then you kind of the middle band is some places called discontinuous permafrost. So there's patches of it and significant amounts of it, but it's not all frozen. And then you go north through the Brooks Range, and all that is permanently frozen. It can be like a kilometer thick frozen material. And then, sure, you're like, okay, frozen ground, what's the big deal? But the thing is, a lot of this frozen ground is 60% water content. So you can imagine when that melts, what it does to your infrastructure. And trying to build a road on it, which adds heat, something you want to do to something that's ice rich. So there's a lot of reasons to understand this more. And then around Fairbanks, there's a fair bit of permafrost. If you don't build your house correctly, I mean, your house moves around, becomes a place that's uninhabitable. And your septic tank fails, there. Okay, so back to this project. It was federally funded. And the airborne, the geophysics, the electromagnetic data, is one of many data types. There's drilling, there's frost probing, there's geochemistry, runoff measurements, you name it. They're doing every sort of measurement to characterize the system. So it's really nice. So compared to a lot of the other data in our collection, the data is fairly dense. It's optimized for like sort of almost like the deposit scale, which you would be interested in, as opposed to sort of here's some more regional data that we can supply you for free. And we have all these complementary data types, so we can actually maybe have something to put the geophysical models in bigger context. So, like I said, it's just behind Fairbanks. I'll show you a map in a minute. So it's highly populated. So created kind of a difficult, challenging environment with data, the airborne data, and the public's actually super supportive of this. They're really interested in it, and we've had many public meetings, and they're really well attended. And so we have, for this project, unlike our mineral exploration project or the mineral support data, we're really focused on just getting the data out. This project had an end game, has an end game, we're still not there yet. Both full interpretations, and in this case, we really had to do some of the more advanced modeling. We've seen some of these case studies earlier. We had to conduct that on the data to learn more about it. And also, we were doing a bit of gravity survey there. And so our goal really is a 3D permafrost map. And not only to the project, but you can imagine that homeowners are interested in it. you can imagine if you're a placer miner, we saw an example where, well, there's two things. It's nice to know whether or not your gravel is frozen or not if you do know you're in an area that has good grade and or maybe the depth of fill, which you may or may not be able to tease out of the geophysics data. In Adam's case, he showed there wasn't an awesome contrast, but maybe there would be depending on your geologic setting. So data definitely has benefits to other stakeholders. So here's a map of the survey. Fairbanks is labeled, the town of Fairbanks is down there at the bottom. And then you just go up over the hill, and this valley back here is Polk Valley, it's the Golden Stream Valley, and the whole watershed to survey up. So we're fortunate to have 100-meter line spacing. This is the CGG resolve system. So it was really nice, data coverage. And the areas outside of the flat-lying valley where there's the hills, we spaced it out to 200 to save costs. And the other thing is we got to fly within 200 feet after a lot of negotiation with FAA, 200 feet of the homes. So it made a survey certainly in this core area possible. At first we weren't even sure we could get a survey. So if you happen to be needing to do a survey in concrete areas, yes, it is possible, it is legal, and the rules are there for it, but you do have to work with your FAA office to get it done. Okay, so now I'm just going to show some fun data from that. We've been seeing a lot of models today. I'm going to talk a little bit more about some of the results and show you something. So here, this is a cross-section. These are 1D models put together to make a 2D model that we're looking at. Horizontal axis is distance, vertical axis is depth. Red is conductive, blue is resistive. You can see this. We have a little conductive cover here, maybe it's the active layer. We did fly this in winter, coolest part of winter. We wanted to have as much as the liquid water frozen up, at least on the surface, because we wanted to have the best depth of investigation as possible. So it gave us a better opportunity to see deeper by producing all the free water in the area. As Adam had mentioned, the conductors are what takes the energy, and that also limits your depth of investigation. So back to this cross-section, it's really neat. So this resistive area, it's a nice, slightly north-facing hill, really nice frozen ground area shown. And then I did this is something I was going to throw out to the public, or I did. So I just labeled these conductive areas as not permafrost, not really taking the interpretation any further. And we have a valley full of these cross sections, and we've actually had some public meetings where I'll navigate people to the cross section below their land or the area they're interested in. And the general public really finds these pretty fascinating. Okay, I'll just give two more examples. This one, over here on the right, this is Smith Lake. It's on the University of Alaska Fairbanks campus. And this is a lake here outlined in blue. And it's known that the ground is completely thawed under the lake all the way down to the valley fill. So you see a nice conductor coming here. And on either side of the lake, you see the blue areas, and that's all frozen ground coming in. So you can see that lake's probably really old, and it eventually produced enough heat to thaw through the permafrost. On this other side here, let's step over a little bit. This area, we know it's permafrost. It's a permafrost tunnel, and this little conductor up here is called Fault Lake. So in that case, the lake is just perched on the permafrost. This brings up an example of you basically see this resistive area all the way to the bottom of the electromagnetic data. But we really don't know where the bedrock's coming in. And that's because frozen permafrost and a lot of bedrock, hard rock, like certain metamorphics and intrusives, they're all very resistive. So you don't know where the bottom is, and that's where maybe you want to consider a complementary method. I talked about doing a gravity survey in addition to figure out the depth of fill. And that's something we are doing for this project. Okay, so then I showed this earlier in the example, but I'll bring it to light again where we're going with this. We've done all these 1D models now. So we took them and we imported it into a program called GoCat. And then we gridded those in 3D, so now we have a 3D volume of all the resistivity from our model. And that's where we're going to try to get out, certainly in the valley bottom here, which runs around here, to try to extract sort of a boundary of the permafrost from the data. We're going to use other data to help guide it. We're going to use our gravity survey. We're going to use drill holes in the area. Just that way, certainly we're going to produce a permafrost map from this with a lot of caveats. Like we just use these cutoffs and made this approximation, but we don't have a drill hole everywhere in the valley, so we can at least get a picture of permafrost, maybe not an exact one, but it gives a good idea. And just to give you a zoom, like, okay, just looking at this area, I might have said this earlier, but zoom into the 3D model, you look at kind of 2D section, you might interpret the conductive area as thawed, and then the resistive area in blue there is an area that's frozen. I'm going to show another area in this data set. So you see that orange rectangle over here is the Wayne Road area. And I'll show another product from the inversion. So here's an aerial view of that area. I'll talk a little bit about it. This is north-facing slope going downhill. This is the valley bottom here. In cold environments or northern latitudes, most of us experience a temperature inversion. So the valleys tend to be the coldest area that would support the most frozen ground. So and that's where you see your permafrost. Not only it's also full. And also from the air photo, you can see something. Just a little. You can see these light areas here, and those are indicative of tussock development. It's this sort of ground that you never want to walk on, and that's indicative of healthy and cold permafrost actually. And another marker is spruce forests, which come up here on the edge. You see the darker, and that's another sign that you're in permafrost, so black spruce. So you can see already from just the air photo, of course, lakes are going to be the warm areas. We saw an example of one that was thawed. And this is coming up kind of a south-facing slope, so it's going to get warmer as you go up.
Question?
Yeah.
Where are the pingos in that picture?
That's a good question. I don't remember where the pingo is.
There's a pingo.
There's a pingo somewhere out here. And those who don't know what a pingo is essentially this mound of ice that forms in a cold region. So you have some groundwater flow that comes in, and the water finds a way through the frozen bed. It's under pressure. Actually, a lot of this whole valley, the groundwater is, if you punch a hole through the permafrost, it's under pressure. And it comes out and it's cold enough. Just until recently, Fairbank's mean annual temperature was below freezing. It's just sort of broke that boundary soon. So that's what formed permafrost. It's all old, it's not new. And so the water comes up and freezes, and you get this sort of giant mound that's super ice rich. Really weird, interesting looking geologic feature, just because of this broken. And there are a few of them. I think they're somewhere up along here. Now you can see those. Actually, it's in the. I might have to show this talk because you can't see those in the data. Talk might get pulled up after all because you have a great example of pingo in that data. So back to this area, I'm not going to focus on pingo here, but I'm just going to focus on these two courses I've done. This one you can see kind of transitions from the treed area into that area called colder. And then down here is just houses, which is the greatest place to have a house. And then some lakes. So that's the surface resistivity. Right away you can see that these areas correlate with this vegetation type. So that's why it's great to use complementary information. It's geology, hand samples, surface samples, in this case an airflow is really useful. And here you can see the more disturbed areas actually a little more conductive. Now we've taken that 3D resistivity model and now we've stepped down 15 meters from the surface. And now you can see we're out of kind of the seasonally active layer. Even the really cold areas thaw a little bit in the summer. Sometimes it's just a meter. And then some of these other areas is much deeper. And you can see we're getting into some older regions indicating frozen ground. And here also, suddenly it shows up a little more clear down at 15 meters. And then by 30 meters down, you're in both areas, are definitely solidly into some nice, stably frozen soils. And here it's just extremely resistant to high ice surge, no free water. And then by 55 meters, the area that had thinner permafrost, you're back into the more conductive sediments that are now thawed, and they have free water in them. And up here, certainly here, it's all the way to the bottom, it's frozen, and kind of transition zone there as you go up the slope into less frozen ground.
Question?
Yep.
So could you use that map to determine the areas of artesian water?
Yes and no. I think you could put a bet on the really well frozen permafrost as being a great cap, and potentially having, and it's thicker too, so you potentially have more pressure underneath them, whereas the thawed areas have some pathways for the water to come back up. And certainly in combination with knowing, I think using the map would be a pretty effective way to predict where you would, especially get into trouble, essentially say, don't drill here. Or I mean, if you know what you're after, you do. Just an aside, the project actually noticed that, because they're trying to figure out some of that hydrology too, like some of the lakes seem to either, the water seems to come like from two different sources. You know, sometimes it comes from surface, sometimes it comes from deeper. It depends on the time of year which hydrology wins, which is kind of neat. Go ahead.
Do you also mean drilling to kind of confirm?
Yeah, so that's part of it. We've had to have some drilling where, because it'd be nice to calibrate some of this, because the depth you never know. And so we do have some drilling, and we're just getting to the point where we can start correlating that to the geophysics. Fortunately, drilling is pretty expensive. I'd love to do more than they did, but there are a fair bit of existing wells out there. In fact, there was a private landowner that came to one of our public meetings and was planning on drilling on his property. He was really keen to see the cross section. I said, well, a lot of times you're supposed to report your drill results, make it publicly available, but this Fairbanks doesn't always happen that way. So I was really keen to get that data back because I can know where certain breaks were and kind of use it throughout the data set. But most the better public, of course there's not much drilling in undeveloped areas here. There's a little bit, but a lot of the homes have publicly developed wells, and then there's some other studies that were done in the 50s. They actually got some funding, which is good because they'll report the frozen intervals and the material type. Because even the frozen silt and the frozen gravel will have different properties.
Could you use something like radar to calibrate? Because it would go through the ice, but then would hit water. You'd be able to map that boundary, I think, reasonably well.
Well, this is so, it's kind of like a muddy, silty environment. The radar just doesn't go anywhere. So you kind of have to drill, or, you know, the top active layer, which is top for the EM system has a problem. The first, Adam alluded to this, but the first few meters, it's hard. You kind of blow through that first bit. You don't get much resolution there. So sometimes I'm going to say frost part of it. When the conductive layer is thicker, 5-10 meters, you can kind of drill pretty well. But you can't really do that. And then the bottom, like I already mentioned, where we just don't know where the bottom is, where we have to switch to gravity. So, yeah, it's definitely neat. A lot of caveats as to where our assumptions lie based on the limited drilling we have. We do have this little bit happens to be over the pipeline, so there's some pretty good data there. We get to look at it. Can't really publish it, but helped us. That's where we really started to get a good picture of, even some of these sort of this, I'll call it moderate resistors, kind of in the middle of it. We know could be frozen because we correlated the model to the drill results there. And it's still frozen, but you can tell it's degraded. You can tell it's the slopes that are failing. It's the houses that are moving around the most, where you can see the really, or whatever it might be, the road that's falling apart the most. Yeah, you don't think about permafrost much until you drive from here to Fairbanks, and suddenly that bump that gets you through the roof of the car will probably actually drive you over some permafrost. That's just really wrecking the road. And so that's where you can see it in there, that the stuff with the least free water is the really resistive stuff. It tells a nice story, actually, that area that I just showed. We gave it to Alex. Yep, they're still falling apart, sorry.
Can you get insurance coverage for that here?
Just got to build your house right. If you build your house, and this is kind of a side, but if you build your house in pillars, and you make it so you can jack it, and you don't add any heat below you, and it's kind of funny, then you're in pretty good shape because you don't change it. I mean, the climate is changing, and the permafrost, it's been for a while, the permafrost has started to melt. Not just right now, but that's accelerating, of course. You're in pretty good shape, but roads and putting a concrete pad down and building your house on it. And people do this all the time. That's why it'll be interesting because this data is going public, and those cross sections. It doesn't take everyone in the room is they can look at a color picture like this and kind of figure out where their house is and think, oh, okay. It's pretty clear, yeah, you don't know that, like he said, to be drilled, you know the depth exactly. No, you don't, but it's pretty clear that you know what you're on, especially if you're in fill. And it has, this color, it's pretty clear what's going on. So it'll be, all of these models are actually, I'm going to publish them. They're just going out, and they'll be downloadable real soon. And Ken's right, though, like, this kind of brings the point, like, there's a trend that probably more of this type of data will be thrown out there with the surveys as it becomes easier for us to make these data. But just because I throw one model out there and let you download it, doesn't mean you should run with it. So you should really think about it. Some of it's fairly easy, but you can see that some of it's not so easy. And I kind of cheated it a little. It's the valley is pretty easy to figure out, but when you get into the hills and you have the resistive rocks and maybe thin cover, and maybe as Ken said, the regolith. I mean, the rock is just crappy in a lot of Alaska. So figuring out what's frozen and not is a little trickier in the hills where you don't have just this sort of frozen fill, that's like the easy stuff to interpret. But you can see, I've seen other examples of data where you have a conductive bedrock and it's all broken up. You get a resistive cap on it, and that's due to the fact that it's frozen. The water infiltrated and then it froze on top. That's still pretty neat. Okay, so where was that? Yeah, so now I'm just going to show another example, and this is another one of our data. It's not as nice. It's 400-meter line spacing. This was done in 2006. This is an example along the Alaska Highway. So this actually came to me from USGS. It's our data. They worked on it. So it's an active landslide. The highway was rerouted because it was falling down. And they did that in 2004, long before the geophysics surveys. They already knew it was a problem. This is again CGG resolved data. And geophysics was one of many data types that were used to look at the slope. And there's some resistivity models that were created by Minsley and I'm pushing them to publish those because I think there's actually, that data covers areas that are interesting for mineral exploration too. It's not, even though it's a long corridor, it's a pretty big survey. Here's just a picture of it. You have a lake, and you have this landslide area that's kind of falling down, and the roads were rerouted. And there are some drill holes here, because I talked to, it's a little bit funny how the academic and government world works, because Hubbard actually is listed here. He's my coworker at DGGS, and he hadn't seen the resistivity models, but he had done the geotech work on this landslide. So this is probably LiDAR, because it looks really great elevation data. The landslide is outlined there. The road is this red line. You can see kind of the old road that was falling apart down there. And this is the flight lines. So we've got a couple in the area. It's not the best coverage, but it's nice to have. And then I want to, since we keep getting it's kind of permafrost questions. This pattern, if you see it in the LiDAR, that's called polygonal ice wedges, and those are super ice rich. So that shape is indicative that those little lines are where there's just massive ice essentially. And we'll keep an eye on those in the resistivity models because they're pretty. Okay, so here's the surface resistivity model. Resistivity is blue and purple, conductive is red again. And so you see most of the landslide is pretty conductive, indicates it's either warm, has a lot of water in it, it's, what I'll say is like it's falling apart essentially. You can see over there though, the ice wedges in the corner, that's very resistant, it's still pretty cold. And the water's well locked up, so. Then we'll step down to 10 meters, I think it's 10 meters, yeah. And once again, this whole area where the road's having problems, pretty conductive still. And I asked my coworker about this, like, so have you drilled this? Is it frozen? He said yes. And this slide at 20 meters tells a story that we've kind of mostly gone through the active layer, at least on that slope. And at this depth, it's all still pretty well frozen. It doesn't matter, just the top of it's moving because it's thawing. So. And then at 50 meters, you're into the sort of the geology response now. You're back down through the frozen bit and you're back into the geology response. And you can also see even the ice wedge area over there on the left is more conductive. And I'll just show a couple, I couldn't put a feeler out for just a couple of sort of general examples of applications of airborne to other hydrology things, and Berkmansley gave me a few examples from USGS. So here's, this is a project in southern Florida, a map over there showing the extent of the survey. And then here, I'm just going to assume it's either apparent resistivity, or depth equals 10. So it's resistivity model 10 meters. And red's conductive, and blue's resistive, and basically that red zone is mapping out the seawater intrusion into the freshwater. So you can see how far the seawater is inundating into the aquifer there. It's a pretty nice contrast between the seawater and the freshwater. So you get resistivity contrast. It's a pretty effective tool at mapping that out. And then this is just kind of a 3D view where they have a bunch of airborne EM data and they're looking at mapping an aquifer. So I'll just zoom in here. And so they're probably mapping, it's probably fill on top of bedrock. The bedrock is blue, and then the fill is the reds and oranges. So you can get a good geometry of an aquifer basin there. And this is in Nebraska where obviously water resources is a big issue. Okay.
Is that surface or is that at depth?
This should be ground surface, all that stuff. So that should be the ground surface, and then I don't know how. I'm just guessing it's probably frequency domain is. We're talking 1,500 meters thick. And here's just a zoom in of one of those cross sections where they have some drill hole data, and they picked out. Basically, they're comparing geophysics and drill hole data and picking out the bottom of the aquifer, the bottom of the sediments. And I stole these slides, so I'm what they did is this study, they ended up changing the interpretation of aquifer bottom based on their models and then compiling all the data. So they have the little line here is the black, and basically they put it all together and they came up with a much better base of the aquifer, so helping manage the resource better. I'm assuming they handle this over the water resources. It's kind of a nice view of just modeling out that. It's a little different than targeting, but still another great application of data. So that's all I have for that. Maybe I'll pull, I got a second, I'll pull this Pinko example since I got asked for that.
What sort of frequencies were you looking at? Were you looking at the high and low frequency data?
Oh, there to make those cross sections, yes. So you need all of it. Or if it's time domain, you need what they say is early and late time to get that depth information.